This video is about supervised learning. Supervised learning is the most common type of machine learning used in real projects. It's called supervised because we learn under supervision. We already know the correct answers for many examples, and the model learns from them. The core idea is simple. We want to learn a mapping from inputs to outputs using labeled examples. A mapping just means a rule when you give an input. The model produces an output. Labeled means the correct output is provided in training data. The true goal is not to do well on examples we already have. The goal is to predict correctly on new, unseen data. If model is perfect on training but fails on new data, it's not useful. In real life, we care for future and unseen data. In supervised learning, every example comes with an answer. That answer is called label. Think of it like practice questions with answers key. This teacher-student intuition is very accurate. The teacher provides question and correct answers, and student learns a rule. The model studies many solved examples, then try to solve new ones. If students memorize the answer, it may score well on the same sheet, but it might fail on new sheet. When new questions will be shared in question paper, so there are chances that student failed. Learning means understanding the pattern. Suppose in maths paper, student learns with the question and answer and got the intuition behind the understanding. Then student will able to solve when the math problem is same or similar but the values are differ. A supervised data set is written as a pair of x and y. X is an input and y is correct output. That is my data set. Pairs x and y. So you can imagine a table. Each row has input information and the last column is the label. That label is what we want to predict. X is called features, Y is target, label or output. This is the correct answer for that example. Example to show you different supervised learning problems. Spam detection is classification. House price is regression. Image label is my classification with many possible classes. We will deep down in these topics in upcoming videos. Now I'm sharing some examples. Like for house price model, features can be the area, number of rooms, and features are not the answer, they are clues which is going to help us to derive the price of the house. So I'm using one training example. There is an input x, a true answer is y, and model produces that we call prediction. We denote it with y hat. This y hat symbols means model's guess. The whole learning process is about making y hat close to y across many examples. So the model takes x and y and output y hat, and we want y hat to match y. Sometimes y hat is number, sometimes y hat is probability, and sometimes it's a class label. But the goal is always to match the truth. The diagram shows supervised learning pipeline. Input goes to model, model's outputs prediction, and we compare with the true label. That comparison produces a learning signal. Without labels and comparison, the model would not know that it is correct or wrong. So we require model as a function that can predict. And we compare that prediction with my real value. Let's deep dive what model is. We can say model is a function. We can write it as a y hat equals f of x with parameter theta. Parameters are internal knobs of model. Training means finding good parameter values so that model will produce a good prediction. In few examples you might have seen this theta or w. That means same. The representation is quite different. Now we have to see like how this model is going to be like trained. So training is the process of choosing parameters so prediction can improve with time or with many data sets. In other words, training is not magic. It's just a searching for parameter setting that reduce error on training data. To minimize mistakes, we need to measure how wrong we are. That measurement is called as loss function. Minimizing mistakes is equals to learning. Loss takes prediction and true label and output a number. Smaller loss mean better prediction and larger means worse prediction. Loss tells us like how wrong we are, and that need to be minimized with the time. writing this loss as y hat and y function. Loss intuition, it's like a penalty score. Like correct prediction is small penalty and wrong prediction is like higher penalty or bigger penalty. This actually helps us because model can use this penalty and improve. Like without loss function we cannot guide learning in a precise direction. Suppose my model is predicting the house rent wrong, then we have to let's see this example. Like regression often uses squared error and different tasks uses different loss functions. We will not deep dive into cross entropy today, but remember, like classification loss usually cares about the probability confidence, not just right or wrong. So for classification it's going to be a log loss function, which I call cross entropy. So we will later on in upcoming videos study this. Now training loop, I'm giving a high level understanding here. So this training loop start with a model and predict like for each example and compute loss, update parameters and repeat many times. So step 1, pick model and then initialize theta. That can be a random value. For each step, example xy, we need to predict a y hat. And compute loss. So according to my loss, theta will going to update and this process is going to repeat with the time until we are able to achieve minimum loss. So that's our target. So let me draw a simple diagram here. This xy predict y hat leads to like computation of loss, and this is going to be give an updated theta, and then the cycle repeats. Think it of like as a improving a skill with feedback. The prediction is your attempt and the loss is feedback score. And the parameter update it adjustment you make so that next time you will be slightly better. Goal is not a perfect training. This is very important point. The goal is not perfect training means the real goal is a generalization. Meaning the model should perform well on new data it has never seen before. If model only performs well or good on training examples but fail in real world, so it's not useful. Training data is like practice question and that same maths example. We don't want our model to just memorize. This should not be the case. Good training leads to, in like upcoming unseen data, a good prediction. Now let's see underfitting versus overfitting. Underfitting means model is too simple. It cannot capture the real relationship in data. So it performs poorly even on training data. Meanwhile, overfitting means like it's too complex. It try to fit extremely well in my training data set. But it learns a lot of noise, random details. So model training performance look great, but in real it is worse. Like on unseen data, it's not going to work. So we need a balanced approach. If both training and validation performance are bad, it's usually underfitting. If training performance is very good but validation performance is worse, then it's overfitting. The best situation is when both training and validation performance are good and not close to each other. Why split data? That's another question, and we want to think in perspective of generalization. If we train and evaluate on same data, we may fool ourselves into thinking that model is good. But that score can be overly optimistic because of the model has seen those examples. Splitting creates a fair exam. Training data is for learning. Evaluation data is for checking whether learning transfers to new examples. This is why fair train and test split and cross validation are standard practice in machine learning evaluation. Now see another concept: train, validation and testing. Train set is used for, I'm talking here about data set only, so I split my data set into this three section. Train set, let's talk about it, used to learn model parameters. My validation set is used to make choices like selecting model settings or tuning hyperparameters. And test set is used only at end to report final performance. The test set should stay untouched during model development. So that's how we can check like is my model is working fine or not, because it's unseen data set. Here is very simple. Train is for learning, validation is for decision making while building the model, test is for final reporting. If we keep checking the test set again and again, we start indirectly tuning for test set, and if we don't realize it, it's going to be we are not going to able to test in the sample set. So parameters versus hyperparameters. Parameter values learned from training data. For example, weights in linear regression or logistic regression are parameters. Example, weights in linear and logistic. Whereas hyperparameters are not learned directly from data. By training updates, hyperparameters are chosen by us, like KNN, maximum depth of decision tree, or C or gamma and SVM or regularization strength. Another way to say it, like parameters are inside the model and get updated during training, whereas hyperparameter control the model flexibility. Because hyperparameters are choice, we should tune them using validation and cross validation, not using test set. Data leakage. This happens when model gets information during training that it would not have at real prediction time. So leakage can make an evaluation look result excellent, but once deployed, performance dropped badly because model was trained on unrealistic setup. A simple way to test understanding of leakage, the model is secretly giving hints from the answer key. Like one common leakage is when feature directly contains the target or future information. For example, if we are predicting whether a customer will churn next month and we accidentally include a feature that was recorded after churn happened, the model will look amazing in training but fail in real life. Also,